For over 160 million years, dinosaurs dominated land ecosystems, not as a single static group, but as evolving lineages that adapted, reorganized, and diversified across shifting continents. By the end of the Cretaceous period, around 66 million years ago, the Earth had already taken on a form that feels increasingly familiar. The great supercontinent had long since broken apart. The Americas were separated, but still taking shape, while Africa, Australia, and Antarctica lay near their modern positions, and India continued its slow drift north across the Tethys Ocean. Sea levels remained high, flooding continental interiors with shallow seas, but the overall geography no longer resembled a distant alien past. The climate, while generally warmer than today, was not uniform. Polar regions supported forests rather than permanent ice sheets, and there is no strong evidence for large, stable ice caps at either pole. Yet seasonal variation persisted. In higher latitudes, months of darkness alternated with periods of continuous daylight, and temperatures could still fall below freezing in winter. This was a greenhouse world, but not a static one. Across these landscapes, ecosystems had reached a high level of complexity. Flowering plants had spread widely, introducing new ecological relationships. Insects such as bees and early pollinators diversified alongside them, shaping patterns of reproduction and plant distribution. Dinosaurs fed within these systems, some browsing low vegetation, others reaching high into forest canopies, while predators moved through the same environments, responding to the structure of prey populations. Birds already distinct as a lineage of theropod dinosaurs occupied aerial niches. Mammals, though generally small, were diverse and adaptable, filling roles as insectivores, omnivores, and occasional predators. Together, these organisms formed interconnected systems that were stable on a global scale. There is no clear sign that this world was about to end. Across this late Cretaceous world, life unfolds on every scale, from the movement of large herds across open floodplains to the quiet activity of small animals beneath dense vegetation. In western North America, one of the most studied regions from this time, large theropods, such as Tyrannosaurus rex, occupied the role of apex predator. Fossil evidence suggests an animal adapted not only for strength, but for perception. Forward-facing eyes that allowed depth judgment, and nasal structures indicating a well-developed sense of smell. Its exact behavior, whether it relied more on active hunting or opportunistic scavenging, remains debated. But its ecological position at the top of the food chain is well supported. Moving through the same environments were heavily armored herbivores such as Ankylosaurus. Its body was protected by dense osteoderms, bony plates embedded in the skin, and a tail modified into a reinforced club. Rather than depicting it as constantly engaged in combat, it is more accurate to understand these features as defensive adaptations within a landscape where large predators were present. Other herbivorous dinosaurs show very different strategies. Pachycephalosaurus, for example, is recognized by the thickened dome of its skull, which may have played a role in intraspecific display or physical interaction, though the exact function is still under study. Its dentition suggests a primarily plant-based diet, possibly supplemented by small animals, reflecting a degree of ecological flexibility. At a much larger scale, sauropods, such as Alamosaurus, represent the upper limits of terrestrial body size. With long necks and relatively small heads, these animals were capable of feeding across a wide vertical range, accessing vegetation unavailable to smaller herbivores. Their presence implies an environment capable of sustaining vast amounts of plant biomass over extended periods. Yet these large dinosaurs were only part of the system. Closer to the ground, small mammals moved through leaf litter and burrows. Although rarely preserved in complete form, their teeth and jaw fragments reveal a surprising diversity. Some adapted for insect consumption, others for more varied diets. Their small size, rapid life cycles, and behavioral flexibility allowed them to occupy ecological niches that required less energy and offered more protection from larger predators. Birds already established as a distinct lineage of feathered theropods occupied the air above these landscapes. Some likely resembled modern ground birds, while others were adapted for perching or gliding. Their presence adds another layer to the ecosystem linking terrestrial and aerial food webs. Taken together, these organisms formed interconnected communities shaped by resource availability, environmental structure, and evolutionary history. Nothing in the landscape suggests that this day will be different. Across lowland floodplains and open woodland, herds of large herbivorous dinosaurs continue their gradual movement through the landscape. Trackways preserved in late Cretaceous sediments suggest that many of these animals traveled in groups, not necessarily in tightly coordinated formations, but in loosely structured aggregations shaped by access to food and water. Their pace would have been steady rather than hurried, constrained by body size, metabolic demands, and the distribution of vegetation. Feeding itself was not a continuous process, but a cycle. Periods of movement alternated with periods of browsing, as individuals selected plant material at different heights and of varying nutritional value. In environments dominated by flowering plants, ferns and conifers, this created a dynamic pattern of resource use, with different species occupying slightly different ecological roles, even within the same area. Elsewhere in more densely vegetated regions, or along river margins, predatory dinosaurs were also active. Whether an individual predator was engaged in active hunting at any given moment cannot be determined directly, but the structure of these ecosystems suggests that opportunities for feeding were intermittent and often unpredictable. Movement through these environments required more than speed. Vision, olfaction, and spatial awareness all played a role in locating prey, avoiding competition, and navigating complex terrain. Mammals forage within dense vegetation and underground spaces, taking advantage of shelter and varied diets. Early birds move between ground and canopy, while insects continue to regulate plant reproduction through pollination. There is no indication in behavior or in the structure of these interactions that anything unusual is about to occur. No shift in migration patterns, no disruption in feeding, no signal, biological or environmental, that distinguishes this day from those that came before it. The structure of the day remains unchanged. In forested regions, activity continues under a dense canopy of mixed vegetation. Flowering plants, now well established, grow alongside conifers and ferns, creating layered habitats that support a wide range of feeding strategies. Herbivorous dinosaurs move through these environments with familiarity, selecting specific plant types rather than feeding indiscriminately. Their choices are shaped by nutritional value availability and competition factors that have defined their behavior over evolutionary timescales. Among them are smaller individuals recently hatched or still growing. Evidence from bone beds and nesting sites suggests that at least some species exhibited forms of parental care, whether through nest guarding or remaining in proximity to offspring during early development. These interactions are not constant or uniform across all dinosaurs, but they indicate that reproduction was not simply a passive process. Survival at early life stages required protection, timing, and environmental stability. Toward coastal regions, the landscape opens into lagoons, estuaries, and shallow marine environments. Here, the boundary between land and sea becomes less distinct. Dinosaurs may approach these areas to feed or drink, but their interaction with marine life is limited by physiology and habitat. Marine organisms, such as ammonites, remain within the water column, forming part of a separate but connected ecosystem dominated by fish and marine reptiles. These coastal systems are dynamic. Tides shift sediment, water levels fluctuate. Nutrient exchange between land and sea supports high biological productivity. Terrestrial and marine ecosystems intersect, but they do not fully overlap. Across all of these environments, forest, interior open plain, and coastal margin, patterns remain consistent. Animals feed, move, and rest according to established rhythms. Juveniles remain close to areas of relative safety. Predators continue to navigate spaces where encounters are possible but never guaranteed. There is no escalation, no deviation from expectation. The system is functioning as it has for millions of years, complex, adaptive, and stable. In one part of the landscape, movement begins to concentrate along a narrow corridor between forest and open ground, a transitional zone where animals moving between feeding areas become more exposed. At the edge of this space, a Tyrannosaurus rex advances with controlled, deliberate motion. There is no urgency in its pace, Each step is placed with care across uneven floodplain sediments where soft ground can absorb weight and vegetation can either conceal or reveal movement. Its body remains balanced, while the head shifts slightly, adjusting to distance, light, and subtle motion within a complex environment shaped by terrain, plant density, and shifting visibility. Further ahead, a group of Edmontosaurus moves through the same corridor. These herbivores feed while in motion, distributing pressure across the landscape rather than remaining in one place for extended periods. Their awareness is uneven. Some individuals pause, lifting their heads to scan, while others continue feeding, relying on group dynamics rather than constant vigilance. This staggered attention creates brief windows of vulnerability that appear and disappear without warning. The distance between predator and prey closes gradually. Encounters like this are shaped by small, shifting variables. Wind direction may carry scent forward or away. Light filtering through vegetation can obscure movement or reveal it at critical moments. Sound travels unevenly across open ground and dense foliage. There is no fixed sequence, only probabilities, influenced by conditions that change from moment to moment. If detection occurs early, the group begins to reorganize, increasing distance through coordinated movement. If it comes late, the situation compresses into seconds, where reaction replaces anticipation, and outcomes depend on immediate response. There is no guaranteed outcome. Even with size and strength, success depends on timing, terrain, and response. Injury remains a constant risk, influencing every movement and decision. Encounters like this likely happened, though the outcome would vary. And here the system continues, stable, continuous, and unaware of what is approaching. From the ground, the system continues without interruption. Across forests, floodplains, and coastal margins, patterns of movement and feeding remain unchanged. There is no shift in behavior, no indication within the biosphere that conditions are about to change. What is approaching does not originate from within this system, and its earliest effects are not biological, but physical. High above the planet, an object enters the upper atmosphere. Its diameter is measured in miles, its velocity in tens of miles per second. As it descends, the surrounding air cannot move aside fast enough. Instead, it compresses violently in front of the object. This compression generates extreme heat, raising temperatures to thousands of degrees and producing an expanding envelope of ionized gas. A rapidly brightening object would have been visible in the sky. Its intensity increases continuously as it descends, not as a brief flash, but as a sustained and growing source of light. The brightness would exceed that of any natural object normally visible in daylight, altering the illumination of the landscape below. This is not yet the impact. No shockwave has reached the surface. No thermal pulse has spread across the ground. The ecosystems below continue to function unaffected by what is still unfolding above. The object continues downward, carrying with it energy that has not yet been released. Estimates place it in the range of tens of millions of megatons of TNT equivalent. The target rocks rich in carbonates and sulfates are compressed, vaporized, and displaced within seconds. Near the point of impact, the effects are immediate. Rock behaves like fluid under extreme pressure. A transient cavity forms as material is forced outward and upward, excavating what will become the Chicxulub crater. Temperatures rise to levels sufficient to melt and vaporize both the impactor and surrounding crust. Any organism within this region is exposed to forces far beyond biological tolerance, extreme heat, pressure, and mechanical disruption occurring almost simultaneously. A shockwave propagates outward from the impact site. In proximal regions, it moves faster than the speed of sound, carrying compressed air and debris across the landscape. Forests are flattened. Surface materials are stripped and displaced. The intensity of this wave decreases with distance, but its reach extends across continental scales. At the same time, vast quantities of material are ejected. Rock fragments, molten droplets, and vaporized particles are launched high into the atmosphere. Some escape the immediate region. Others follow ballistic trajectories, rising above the atmosphere before beginning their return. Further from the impact, the sequence unfolds differently. The initial collision is not directly experienced as heat or pressure. Instead, effects arrive in stages, first as seismic waves, then as atmospheric disturbances, and later as falling ejecta. The timing and intensity vary with distance and geography. This is not a single uniform event. It is a cascade of processes, each interacting with the environment at different scales. What begins here at one point on the surface will not remain local. What follows does not unfold as a single simultaneous catastrophe. The effects propagate outward from the impact site, each governed by its own speed and physical mechanism. Shockwaves move through the atmosphere and across the surface. Seismic energy travels through the crust. Ejected material rises above the atmosphere before beginning its return. Each process operates on a different timescale, reaching different regions at different moments. These effects did not arrive everywhere at the same time. In regions close to the impact, the first consequences are immediate and extreme. Air pressure increases rapidly, generating a shockwave capable of flattening vegetation and displacing surface materials over vast areas. Thermal radiation released during the initial moments ignites fires within a broad radius. These fires are not the result of a single flame front, but of multiple ignition points, triggered almost simultaneously by intense heat. Further from the impact site, the sequence becomes more complex and delayed. One of the most significant processes develops in the upper atmosphere. Material ejected during the collision, pulverized rock, molten droplets, and vaporized minerals is launched along ballistic trajectories. As this material re-enters the atmosphere, it compresses the air in front of it, generating intense heat and producing a widespread thermal pulse. This leads to a global pattern of surface heating. Temperatures rise unevenly across different regions depending on atmospheric density, angle of re-entry, and local environmental conditions. In some areas, this heat is sufficient to ignite widespread wildfires. In others, it causes partial burning, dehydration of vegetation, or delayed ignition as conditions continue to change. The distribution of these effects is irregular rather than uniform. At the same time, ocean systems begin to respond to the initial displacement. The impact generates large-scale waves that radiate outward across ocean basins. As these waves travel, their energy is redistributed by seafloor topography and basin geometry. When they reach coastlines, they inundate low-lying regions, transporting sediment, debris, and marine material inland. In some areas, multiple wave reflections and interactions may intensify local flooding conditions. On land, atmospheric and surface processes begin to interact. Shock waves can circle the planet, diminishing in intensity but still capable of disturbing environments far from the impact. Fires spread where fuel is available, merging into larger burn zones. At the same time, fine particles, ash, dust, and aerosols begin to accumulate in the atmosphere, gradually reducing the amount of sunlight reaching the surface. In the years that follow, the planet does not return to what it was. The atmosphere gradually begins to clear, allowing sunlight to reach the surface again. Temperatures stabilize, though not immediately. Ecosystems do not recover as intact systems, but as fragments reassembled from what remains. The structure that once supported large, energy-demanding animals has been fundamentally altered. Survival in this context is not random. It is shaped by biological traits that reduce dependence on stable, high-productivity environments. Smaller body size becomes an advantage. Lower energy requirements allow organisms to persist on limited resources. The ability to consume a wide range of food, seeds, detritus, insects becomes critical. Many of the survivors share these characteristics. Small mammals already adapted to life in burrows and sheltered environments are able to endure periods of low food availability and unstable climate. Their reproductive strategies, short generation times, and high adaptability allow populations to recover more quickly once conditions improve. Certain lineages of dinosaurs also persist. These are the avian dinosaurs, early birds, whose anatomy and metabolism differ from their larger relatives. Feathers provide insulation. Flight, in some cases, allows movement across fragmented environments. Their diets are often flexible, including seeds and small invertebrates, resources that remain available even when larger food webs collapse. They are not survivors by chance, but by compatibility with a changed world. In contrast, most non-avian dinosaurs, along with many large marine reptiles and other dominant groups, do not persist beyond this transition. Their size specialization and energy demands are no longer supported by the altered environment. Recovery begins slowly. Plant communities re-establish first, followed by the gradual return of more complex food webs. Over time, mammals diversify, occupying ecological roles that were once dominated by dinosaurs. The structure of life on Earth is reorganized, not restored. What emerges is not a continuation, but a replacement. The last day of dinosaurs was not a single moment, but the beginning of a different world.